Hello everyone, in this video I'd like to present a JavaScript port of world's smallest chess program. So last video I've been covering the project by Garcia, who has created the world's smallest chess program. That's the Guinness World Record holder kind of project, and I had a detailed video about the original project. But just to remind you quickly, this is the program of 353 bytes, the extended version, and the most minimalist version is 265 bytes. Both are available to play here in this ZX Spectrum simulator or emulator. So you can just input moves like D2, D4, and it makes a move, and it makes response D4, D5, etc. So it sort of plays chess. It's not about playing strength at all. It's not using even the recursive search. It just uses so-called 1.5 ply search, where essentially you rely on the this is the static evaluation without creating a search tree. So just given a list of moves, it just finds the best move, but to make sure that it's not taking a piece that is protected, the attack map is created. So those squares attacked by white pieces are taken into account when calculating the best move for black. So all this is cool. All this is extremely cool. So excited about this project. And it has a very detailed explanation how it works internally, explaining essentially literally every single line of code written in Z80 assembly. And here is the bare source code in Z80 assembly with quite nice commentaries, really nice commentaries, yeah. But what I have created, I made a program that plays exactly the same chess as this one, but it does it in the web browser without any emulators, and it's written in pure JavaScript. Thanks really to Alex Garcia, the author of the original project, I was capable of recreating the exact, I don't want to call it a copy because it's not really a copy, but implementing the exact algorithm that this original program is actually using, including the piece encodings, the board representation, the matter of how to evaluate moves, how the move generation is done, all that stuff, but not in Z80 assembly, but in JavaScript. And the reason behind this is because I want this program to be accessible by as many people as possible, because I personally see a great value in this particular program. So hopefully with JavaScript code, it would be much easier to understand how this works internally. So here is the GitHub page for my port, and you can read about the motivation I had doing this project. Here we have the link to the original project, how to play things, known issues. So because of this so-called 1.5 ply search, it might happen that it would move a pawn away if under attack, if king is under attack. The pawn is under attack, but it protects the king, so it may expose the king into a check just to save the pawn. And also, it might happen that you did give a check to a king, and it might happen that you need to move a pawn to simply protect the king, and that pawn would be protected on its own. But this would never happen because computer would think that it just gives up a pawn for nothing, and it doesn't know that the next move, the king would be captured, and that would be essentially the checkmate scenario for computer. So he doesn't see that far, so he would not try to protect king that way. But he would try to step aside with the king, if possible, just like with any other pawn that would get under attack. So first, I would like to demonstrate you how this essentially works. So this is my version. I'm using Unicode characters to represent pieces and some HTML tricks to have this colored squares. And the input is exactly the same as in the original program, so it just listens to the keyboard input. So I will now just play a game, given a chance to the computer so that you could enjoy how nicely it can play. So let's start with D2, D4. Okay, so far so good. Maybe D4, D5, trying to attack the knight. Okay, now e2, e4. Okay, he moves c5, great. Now I want to develop my knight, so g1 to f3, and he develops the queen. Yeah, so far so good. Now let's say, yeah, maybe I can play c2 to c4. All right, and now if I try to attack the knight by say a2, a3, it drops the knight back, so doesn't want to lose the knight, although his position doesn't seem very good, but still. So let's develop a bishop, so f1 goes to d3, and he improves the position of his queen, which is reasonable. Now let's say I want to play g to g3 with an idea of bishop goes to uh, f4, or maybe I can do c1 to e3 first. Okay, he just puts the knight into a better position, which makes perfect sense. Queen from d1 to d2, and assuming that computer essentially doesn't have a recursive search, but still he plays maybe not very reasonable moves, but still he self-plays. He cannot castle, but you see, like if he could castle, now would be just the perfect timing. So b1 to c3, I want to keep developing my pieces, and he develops the rook, which is so great. Let's say rook a1 to d1. I want to centralize pieces. Okay. Hope that one day he would start to improve his king side. But for now, I think I can play e4 to e5, hits the queen, and he captures because he probably didn't have any other place, because here he would get captured by the pawn, here he would get captured by the bishop, and here he will also get captured by the bishop. So yeah, essentially the queen got trapped. But I will give him a chance. I'm not going to take the queen. I would play g2, g3 just to give him a chance. Okay, and he drops back. And now king e1 to e2. Okay, he starts an attack on an h file. This is good. So say h1 to e1. Okay, now e2 to f1. So artificial castling. Okay, f1 to g1. Yeah, he just moves the rook back and forth. Yeah, since all these squares, many of these squares are attacked by white, computer thinks that he cannot move there. So I need just to give him a piece, probably. Let's give up a knight. So I say knight from f3 to e5. And yeah, he just takes the knight. This is great. Now say if I play bishop from e3 to f4, okay, so he finds a fantastic place for his queen. This is so good, great. So this pawn is protected, so he's not going to capture the pawn at the moment. And let's try b2 and b4. Okay, he's putting pressure on b4. This is good. Now let's say knight from c3 to e2 hits the queen. Queen steps aside. So it's reasonable chess. Yeah, I could have taken the queen for sure, but anyway, this is so interesting. Now let's say king goes to, let's say, g1 to g2. Okay, he takes the knight. Okay, a3 takes on b4. Okay, he doesn't take the pawn back because it's protected by the queen. All good. Now let's maneuver the knight, say e2 to g1. Okay, and he starts an attack. Finally, he starts an attack. Can you believe this is so interesting? Yeah. So I could have put the bishop here to pin queen and rook. That's probably something that I do now. So f4 goes to g5. Yeah, it's not very clear why he couldn't go here, because it's okay. Not going here, it's attacked by bishop's not going here, attacked. He could have come here maybe. I'm not sure why he couldn't go there. I will still give him a chance. I'm not going to take the queen. I play f2, f4. Yeah, so he saves the queen. This is good. And now let's say I play f4 takes on e5. Okay, and he steps aside with the queen. This is good. Now let's say I move the rook e1 to f1. All right. Now I move the queen. So d2 to f2. Okay, I think he just took the pawn, did he? Okay. And now f2 takes on f7. And he takes the queen. He doesn't see that the queen has been protected, and that's by far the best move. But that's not allowed, so f1 takes on f7. And this is the checkmate because I've just captured opponent's king. So maybe not very impressive, but again, assuming the original design that only contains like 265 bytes in here. This is the entire chess program in assembly language, so it's a very tiny one. I think this is incredible result, how it's played. And I also need to mention that some extra time and effort has been spent by me and with the help of Alex Garcia, the author of the original project. He helped me debug in the evaluation function and other things to make sure that my program works and plays exactly the same moves as his version. This one is called Full Features and Look. So it's not the same as this minimal feature and look, but this full feature and look, they're just different from the evaluation perspective, apart from how it looks. So it works exactly the same as this one, right? Okay, so now that being said, let's get to the most interesting and the most exciting part of the entire project is the source code. So I would like to share the source code with you guys, and without further ado, let's get into it. So this is the single HTML file. You can play online like I did in this link, but also you can just download the HTML and run it locally in your web browser, and this is the entire source code. So I need to say that the source code is bigger than the assembly code, because like size coding versus golf coding are not exactly the same thing. So size coding aims to have the as small as possible binary executable, while golf coding looks for creating as small as possible source code, like in terms of the number of characters. So say Micromax by Homgit Müller is the example of the code golfing, while this program is the example of size coding. So these are a bit different things. So small binary executable versus small amount of source code. So because of the fact that what may only take just one byte instruction or a couple of bytes, it may take more text to type in a high-level language like JavaScript. So this cannot be as small as the original program, and also because of memory layout, and we don't have the memory layout in particular in high-level languages. We just have variables, so it's a little bit different than in the original. But again, it works the same way. It's organized a different way, but it works exactly the same way. And also, there is only one loop, and say printboard function has been embedded into the main loop in the original code. Since in JavaScript we cannot achieve the same because the listener to the keyboard is an asynchronous process in its nature. So I was forced to separate the user input to a separate function, render board, also like print board, essentially drawing the board to screen, to a separate function, and the search function, essentially the engine, the AI logic that makes the move in response to a human move, also has been separated. So the chess kind of part is the search function itself, and it results in making a best move on the internal board and rendering the board. So that's how it works. Okay, so let's just go step by step. So in order to make this possible, I needed to read through the entire dissection part from Alex Garcia. This is very interesting reading, and I highly recommend reading through this if you don't understand something in the source code that I'm providing, because these materials present more insights in terms of how the algorithms have been picked up, how they work, why exactly that way, and so on. But anyway, so starting with piece encoding. So I just want to read through this map. So bit 1, this one, I mean bit 0, this one, is always set to 1 for all pieces. So it would be, if that's an empty square, this bit is not used. I think in my implementation, I'm not particularly relying on this because this might be useful when you want to squeeze some bytes from the Z80 assembly to quickly do the AND operation to check the byte. It's faster than making a lookup in the board array. In JavaScript, this is not so. So looking up the board array is not a problem. So I'm sorry, I don't remember. Although I just finished the program, I already don't remember whether I used this bit or not. Anyway, the second bit is the color. So for white pieces, it's set to 0. For black pieces, it's set to 1. Next bit is distinguishing whether the piece is the pawn or not. So only the pawn bit is being set. Okay. Next bit represents slider pieces versus the leaper pieces. So bishops, rooks, and queens. Bishops, rooks, and queens are marked with ones, which means these are the slider pieces. The rest are zeros, which means those are the leaper pieces. Both bits 3 and 4, so these two bits, contribute to a piece value. And bit 6, this one, identifies if the piece is the king. Okay, this one. So this is the king, and this is the king. And meanwhile, bits from bit 2 to bit 6, so from this one to this one, this also serves as the piece value. So this is used for the evaluation purposes, and the value itself is already sort of encoded within this mixture of flags and this couple of bits that contribute to the value of the piece. So this is the most tight piece encoding ever that I've seen in my entire life. So this is extremely tight, very amazing. I'm so excited with this, like probably my best ever loved part in the entire program. Okay, so here we have the encoding being defined according to these principles. So we essentially just define the variables. Then this is the lookup table that converts, again, in Z80, you don't need the object, right? In Z80, you can just have a table of pointers that would be pointing to bytes where the piece values has been stored. And obviously in the original program, it uses like letters, not the Unicode characters. But I decided to use Unicode characters because it just looks better, right? So we can reference corresponding Unicode characters by piece values here. So this comes very handy. Then the board representation, it uses the traditional hexadecimal ATA boards with all those principles, like you can bitwise AND the square with hexadecimal ATA to know whether the square is on board or off board. Nothing new here. We've been doing this like board representations many times before in this channel. So nothing really new here. So this is the board. The right hand side is not used. I thought maybe I could use the right hand side to store attacks by white pieces, and initially I did that, but then I found it quite not that simple to clean up this values, because every time we want to clean up the attack table to generate it from scratch, and hence I decided just to use a separate variable that is used for that purpose, for that sake. It's just easier to initialize that variable. You just create new array and fill it with zeros, just a bit faster. Potentially may lead to memory leaks, but who cares, right? So next we have vector pointers. So this is the table with So the piece code, we do some operations, some bitwise operation with the piece code to extract the value, one of these values. Not exactly. This is done with an offset because offset is needed because of memory paging issue with the Z80 assembly. But I try to mimic this as close as possible. I just do some extra uh, adjustment of the value being extracted from the piece to get rid of, so that it points to the very beginning of the array. Anyway, so we convert piece values to this like values. So it's like as if all pieces were black plus some constant value being added, and then it points to the starting point. So again, not this fa, but then we want to strip f1. So this value minus f1 would point to the index in this list. So it may point, for instance, pawn moves points here. Okay, knight moves points here. Bishop moves points here plus 1, 2. So bishop moves start from here. So essentially this one and this one are the bishop moves. Then rook moves points here. I mean, I'm sorry, pawn moves not point here. Pawn moves points here. It may move forwards and may move diagonally. Yeah, I'm sorry. Knight moves points here. Bishop moves points here. Here and then here as well. When it encounters 0, it just reverses the direction. I will mention that separately. Queen moves starts here, and king moves also starts here. All right. Then some essential variables. So the variable to hold the best move found by the computer, the best score, that move scores during the evaluation process. Move list, where we're supposed to be storing, pushing our moves, so that later we can compare them, look through the moves, and find the best move, and be adjusting the score, just like in Minimax, but without any recursive logic, just as if we were at the depth 0 all of the time. User move is the variable holding whatever user inputs from the keyboard when you're playing in the web browser. So this is the hook to the board div element, view element, so that later we can change the inner HTML attribute of that. And also we add the event listener key down so that when we are in the web page, once we press a button, it gets recognized and it essentially gets stored. So user input is exactly the function that is responsible for this. So every time we click, we hit a button, it appends the key to the very end of the board HTML view. So it goes down below, like if I do like E to E4, when I press 4, it already makes a move, just goes too fast. Anyway, D to D4, so it appends to the HTML from below to the particular board div. Hopefully that makes sense. Then it also populates the variable user move with a particular key that has been input by the user. Once we have the length of the user move equals to 4, that's exactly how it works in the original code. So we don't need to press enter to say, okay, the move is done. So when the length is 4, so you hit the button 4 times and you are done. It doesn't have move validation, obviously. So if you just input some gibberish, it would just skip the move, and after skipping the move, it would just make a computer move anyway, as if white has moved. So hopefully that makes sense. So then it extracts the source and the target square, so essentially effectively converting this algebraic notation like E2, E4 to the particular indexes, assuming the 128 elements board in here. So like we need to convert E2 to the index of this square, E4 to the index of this square. And there is a helper function that helps with this. So parse square is the name of the function. So essentially, we just extract the rank file this way, then extracting the rank, assuming the board ND energy is also important, and then just the classical rank multiplied by the width of the array plus file gives us the eventual square where we want to which we want to reference. Okay, so once we've passed these squares, so we need to make sure if computer always plays black, human always plays white. This cannot be changed. The entire logic is hard coded for this. That's the limitation. But 265 bytes for the original program. You need to understand where the limitation is coming from. So if it happens that the target square the user has specified is black key, so essentially you're capturing black key, this means the game is over. It will give you a checkmate alert, and it would remove the event listener so that you're no longer capable of inputting moves. So you just need to refresh the page, and after refreshing the page, you may try to play a new game. If this is not the case, then it just moves the piece from the source square to the target square, and then it erases the contents of the source square. That's the very classics. In case if we have the target square is less than 8, which means it's the 8th rank, and if whatever we find, the piece that we find on the board target square is white pawn. So say we promoted a pawn. In that case, we want to turn the pawn into a queen. And after all this has been done, we just reset the user move back to an empty string. After this, we render the boards, and now we're ready to ask the computer to search for a best move. So essentially, after user made a move, then the search is called and computer starts calculating. So render board is quite a simple function. We have the position variable which holds the HTML string with all the stylings. Like I'm using spans to highlight squares, and also I'm using this display inline block to make span wider than the actual letter. I could have used divs to wrap around, but this is just takes less space. So also I have this dark square flag. So if it's being toggled, I want to have the dark square. Otherwise, I want to have the light square. I'm toggling every row, every column, and I'm also toggling this every row. Okay. And if the square is on board, then I just ask to print using the pieces, which is like Unicode characters. So Unicode characters object is being indexed by the contents of the board square, and this in return it returns the visual representation of a chess piece. And in case if we are going to the very end of the row, we want to create a new line. So BR tag serves the purpose of creating a new line. Then we want to skip those squares that we're not interested in. So say we come here. So we loop here. Okay, so this is the end of rank. We add BR tag to make this line appear on the new line, and then we just say plus equals square plus equals 7, so square equals square plus 7. We skip this, so we're not interested in this, and then the loop continues from here, and this is done for every single row. Okay, so now the most interesting part is the chess engine itself, chess program. So best score, before anything else has been initialized to 0. Best move has been reset, so it's now an empty list. Move list also gets reset, so nothing in the move list. Attacks is the data structure which is similar in shape to the board. So this is the board array of 128 elements. Every time we fill this array with 0. I believe this probably results in a memory leak because I'm doing this new. I'm not sure if the garbage collector essentially clears up the attacks or not. Maybe I should say attacks equals to an empty list. I'm not quite sure. Anyway, who cares about that? So once all this initializations has been done, we are entering the very main loop. So the main loop is to loop over all the board squares available. So starting from 0 to 128. So this is the variable source square. Later, this variable would be used as the source square of the move created by the move generator. So first thing we need to do, we need to make sure that the square is not off board. So this is the square that is we need to make sure square is in this area, not in this area. So square is on board. That's the first thing to figure out. So we made sure the square is on board. Then we initialize the piece. Piece is whatever contents we have in the board array indexed by the source square. Now, it might happen that the contents is empty, so we're not interested in that scenario. So we say if piece, this means that the contents of the board array indexed by the source square contain something there, and that something would most likely be a piece, hopefully. So that is the piece. Then we want to initialize the vector pointer to know what would be the directions for this particular piece to traverse. So bitwise and in P, bitwise or in piece with hexadecimal 82. I could avoid doing this in JavaScript. We don't particularly need this sort of an operation, but this was used in the original code because of memory paging and to avoid reloading registers to point out to another page, just to make it simpler, quicker, and with less code, with less bytes of eventual binary executable. The pages are organized a certain way so that the locations might seem a bit weird from the high-level language perspective. So again, this is just the legacy from the original implementation, which I just tried to keep traditional as it was done initially. So this is not 100% needed, really. So the idea, so the vector pointer essentially should point to this table. So one of these values. And then as you can see here, I do minus hexadecimal F1. And that's simply because, so I'm doing hexadecimal F1. So this value minus hexadecimal F1, this value minus hexadecimal F1, because this index would be like hexadecimal F1 plus 0 plus 2, 4, and this is not 0, this is essentially 9, I guess, yeah. So that we want these values to be pointing to somewhere in this table where the actual offsets like move upwards, downwards, left or right. So we need to adjust the value. You might be wondering why not to set these values like to be normal from the start. Again, the reason is similar. The legacy of the original code. So I tried to make this to look like the original code. So for those who would be interested in studying the original code, so that you don't think that this is just a custom program that are written from scratch. No, this is the program this is essentially the port of the original program to JavaScript. But because of the original environment, it might look a bit weird. But again, this is the way how I can show respect to the original project by keeping all the mechanisms of lookup as they have been done in the original code. To me, this is very important because otherwise this work doesn't quite make sense to me, because I did write mini chess programs earlier. They even had the minimax search recursively. So, like, it's not about strength or something. This is about to be as authentic as possible. This is one of the major goals behind the project. Just trying to make the original project as didactic as possible by porting it to JavaScript, so that you guys could clearly see how it works. Okay, so after we subtract this value of hexadecimal F1 from one of these values, we then know the index where to start looping over the directions within the vector list. Okay, so say these are the diagonal directions. It can be used by bishops or by pawns. This is direction like front or like up or downwards, it only uses half. It's not using like all, like say for night, it's not using all the 8 directions. It only uses 4. And to come up with the rest of directions, we would be looping in the another direction. So first we loop like this, then this, then this, then this, and then we hit 0. Okay, then we start looping in the opposite direction, going back here, but with a negative sign, going back here, but with a negative sign, here with a negative sign, here with a negative sign. And when we know that we traversed 4 front, then we traversed 4 back. This means that we have traversed all the offsets regarding the night. And that's how we know that we may leave this part and go for a next piece. We'll come to this just right in a moment. So we do initialize the vector pointer. We set up the vector offset to just a value so that this while loop gets entered, nothing much but that. Direction is the variable that is responsible for either we iterating from left to right or from right to left within this particular list. So say we are here and direction equals to 1, it means that we iterate this side from left to right. If say we are now here and the direction is set to -1, this means that we iterate this way. And then the offset count variable counts like how many from the starting position to the 0. So we encounter 1, 2, 3, 4. So offset count is equal to 4. So when we get here, we know that we need to loop exactly 4 times in the backward direction. So we go 1, 2, 3, and 4, and we stop that. So that's the idea behind these variables. So offset count, the one that I've just mentioned. So we are entering this loop over the directions or vector offsets, in other words. So we initialize the offset vector. We use the vector lists pointed by the vector pointer and multiplying by the direction. So if the direction is equal to 1, we have the values as they are, say 1, 10, hexadecimal, 0f, 11. If the direction is negative, then we would be having -1, -10, -0f, -11, etc. This would allow us to move pieces in all the directions available. Say for, let's say for a rook here, so rook goes right and rook goes down. But with -1, rook would also move left, and with -10, rook would also move up. So that's the idea. All that is done for the reasons of saving bytes in the eventual binary executable. An easier way of implementing this without messing up with directions of traversal of this list, you could have said just 1, 10, then comma -1, -10. So this would add 2 more bytes, but it was more efficient when it comes to Z80 assembly. Instead of using this additional bytes to mention the vector offsets, the directions to go through, instead of specifying them, defining them as bytes here in this list, it was cheaper to use it in code to say that we go this way and then we go this way because of reversed loops in Z80 assembly. I'm not an expert on Z80 assembly, so I'm not sure how exactly that is happening, but just to give an idea that that's more efficient from the original program point of view perspective. Okay, then what? Then we have a direction, okay? And in case if we encounter a situation when the vector offset is equal to 0, we just break. Another important thing here is this one. So it might happen, so if the direction is greater than 0, then we increment the vector pointer, okay? And we count the offset. And when it comes that it's 0, okay? then we set the direction to the negative, and just to avoid overflow of the vector pointer. And otherwise, we just would be decrementing vector pointer and decrementing the offset count. And finally, we just break out of this loop. It might seem a little bit complicated, but that's exactly what's happening. So feel free to read the commentaries, and feel free to read the original dissection section of the original program if you don't quite understand how in particular this happened, because the way it's done in that 8 assembly is way more elegant than it's done in JavaScript. JavaScript looks like a weird addition that doesn't make sense and just overcomplicates things, which essentially it is. But again, in the original project, the way it's done is very elegant, very beautiful. So you would fall in love with that if you understand how that works. I promise you that. Okay, so we just know that within this loop, we did make sure that we traverse all the directions, like all the vector offsets, like up, down, left, right, for night, all the 8 directions. Okay, so all the directions. Then when that is done, we do initialize the target square equals to the source square. That's the starting point. And then we enter the loop, the last nested loop, the third nested loop in particular, which would be looping along the squares within the given attack ray. Say we have a rook that has 2 offset vectors like north, south, east, and west, like left, right, up, and down. So say we are moving with our rook to the right. So if this loop wouldn't be there, the rook would only make one move to the right and that's it, it would stop. But the direction going to the right may have many squares for a rook to go. So go right 2 squares, go right 3 squares, go right 4 squares, etc. And then depending on whether the rook hits the board edge or friendly piece or enemy piece, we would decide what to do then. So within this loop, the first thing we need to do, we need to initialize the target square, which would be equal target square plus the vector offset. So say for instance that we have a pawn on e2. This is a given number in hexadecimal, and if we take this number in hexadecimal and subtract 10 from it, it would be the address of this square. So this is how we calculate the target square. If we want this one, we subtract 10 hexadecimal 10 twice, and that's how we know this square. So when we subtract the vector, the particular vector offset of the direction moving upwards, for instance, this would be minus 10. If we do it twice, yeah, then we know that this square minus 10, and the resulting number would be the index of this particular square. That's how we calculate the target square. So hopefully that makes sense. Now it might happen that we are iterating over the squares within a given attack ray, and it happens that we hit the board edge. How do we know that? If the target square bitwise end with hexadecimal 88 results in a positive value, this means that we have just reached the off-board square. That's the nature of the hexadecimal 88 board representation, which you can read about on chessprogramming.org website, which explains this in great details. Next thing we want to do, since we're using the same vector offset lists for all the pieces, if we don't do these 2 lines, then pawns would be moving 2 directions. So pawn would be moving forwards and backwards. We want to restrict that. So we want white pawn only moving upwards, and we want the black pawn only moving downwards. So depending on whether the direction is positive or negative, which means that if it's positive, that we're using the plus offset. If it's negative, we're using minus offset. And this represents also the direction of the pawn, whether it's moving forwards and backwards. So we want to restrict white pawns to moving only forwards, and we want to restrict black pawns to moving only sort of backwards from the perspective of the chessboard. So white pawns only move forwards, black pawns only move backwards from the perspective of the board array. So on the board array, this is the index 0, and this is the index like plus whatever. It's not 64 because we also have 8 here, 8 here, 8 here, 8 here. So it's, I don't know what is this, but so this is 0, and this is the biggest one, assuming the onboard squares, not taking into account the offboard squares. Okay, so we want to restrict the moves for the pawns. Next thing, we distinguish what to do if the piece is black or white. So if the piece is black, generally we want to generate moves for that piece. If the piece is white, we want to initialize so-called attack map to know which squares are attacked by white. This would be later used by the evaluation function. So at the moment, we know that the piece is either black or white. So if we do this bitwise operation, so piece bitwise ended with 2, so this is the second bit, and you remember the second bit is responsible for handling the color of the piece, so the color is encoded in the second bit. So if this results in true, we know that we are now currently traversing through the black piece. In this case, what do we need to do? It's very simple. If it happens that the target square contains a black piece, this means that black piece is about to capture the black piece. We don't want that, so we just break out of the loop, right? Another scenario, it might happen that the piece is the pawn. We use this fourth bit to check whether the piece is the pawn or not. So if this is the pawn, we don't want pawns to capture when pawn does not move diagonally. So pawn only captures diagonally. If it moves forwards, it's not about to capture. Why this particular expression works, I want to reference again the original dissection section here. It's explaining great detail, so even noob like me did entirely understand how that works, and there is a real beauty behind this kind of thing. So instead of me trying to explain this, you better just read through the explanation there, how pawns are essentially moving, and just enjoy how Alex Garcia provided those explanations. Really, real masterpiece. Not only the program masterpiece, but also the explanation masterpiece as well. The most didactic documentation I ever read in my life. I enjoyed that reading so much. Okay, so we skip the illegal moves for pawns. And in this case, essentially, we're ready to push the move into the move list. And one last but not least thing to do. It might happen that our piece is about to capture opponent's piece, enemy piece, white piece. In this case, we first add the square, so that is a legal move to capture opponent's piece. But once we hit the opponent's piece, then we break out of the loop. So we are not going beyond the white piece. So say white rook is moving, and then it encounters a white pawn. So a move where rook takes the square occupied by the white pawn is added to the move list, but no other. So rook cannot go one square beyond the pawn. So this is the idea of this break from the loop. Otherwise, if this wasn't a black piece, this is likely to be a white piece. And in this case, a very similar thing for a pawn. So we only want to use diagonal pawn moves as those to be marked, so those squares where pawn may go diagonally regardless of whether there is a piece or not, those are the squares attacked by the white pawn. So we want to add those pawns, or add those squares marked to the attack map. Okay, and that's exactly what we're doing next. So for all the other pieces, apart from pawns, we don't need any special conditions, just where the piece may go, because the move generation essentially is shared by both white and black pieces. But for black pieces, we use the move generation to push the move into the move list, and for whites, we just use the move generation to mark those squares where white could go as the squares attacked by white, okay? And that's it. So squares attacked by white are also stored. Just the value you use is this hexadecimal 80. It might be whatever non-zero value. Again, this is just the tribute to the original implementation, because the register value of something was by default this one. So to avoid using any extra instructions, Alex has used the value that already was in the register wherever it was. Okay, and again, another quite important thing, if we encounter a piece after we've added mark the square, we just mark the square. So here we add push the move, here we just mark the square. If after that we encounter a piece, no matter if this is black or white, and there was a bug with this, which I've fixed, thanks for to Alex as well. So no matter black or white piece, we just break out of the loop. And if, say, white attacks white piece, this is marked as the attack. If white attacks black, this is marked as attack. In case if later in the evaluation it happens that you're trying to calculate the value of a given move, and you know that currently your piece is under attack, then you try to move out from there to save the piece. Otherwise, if you're looking to capture opponent's piece, how do you know whether that piece is protected or not? If it's been attacked by white pieces, it means it's protected, so you are not likely to capture it. So that's the reason behind white to stop after like we hit any piece. Earlier I was making the program to stop when it hits black piece. I mean, consider when it takes the black piece, but when it takes white piece, not mark that as the attack square. But that led to a weird behavior where engine was capturing pawns protected by other pieces, literally giving up material. So that was fixed, fortunately, and to make it fixed again, so no matter what the piece is, after you mark the attack, you just break. Okay. If we have a leaper piece like a pawn, knight, or a king that we don't really want to loop over the vector offset, so we just want to jump once and stop there. So this line allows this. But there might be an exception for pawns if the pawn is moving 2 squares ahead. So if pawn is attacking the 6th rank, and also if the next square after it is not occupied by anything, then we want to continue, which allows us to generate 1 extra move for a pawn. Otherwise, we just break out of the loop. And that's it. And then the direction traversal code, which I've already explained how it works. So again, we just move to the right side, hit the 0. So we just we land somewhere in here. So say we're generating queen moves, so generating queen move in one direction, another direction, so vertically, horizontally, diagonally to another side, hit 0, okay, time to go back, so direction is no longer 1, now direction is equal to -1, and the loop goes the opposite direction like this, and we traversed 4 elements forwards, we traversed 4 elements backwards. That means that we are done. All the directions for a queen has been traversed. Okay, move on. So this is it essentially in regards to the entire move generation and generating the attack map that is going to be used within the evaluation where we are about to enter just now. So at this very moment, we already have a move list being populated with moves. The way it gets populated is quite simple. So just 2 elements, the source square and the target square. So we loop over all the moves within the move list. The basic evaluation is equal to hexadecimal 7f. Again, that's the legacy from the original implementation, the value that is there already somewhere in the register, so you don't need to initialize it to spend bytes on initializing this. Another reason for this is with Z8 assembly, it's not really that easy or cheap to deal with negative numbers, so we want evaluation to be positive all of the time. So we take relatively big number so that it's almost all it would be FF if the very leftmost bit was 1. Now it's like 0, 1, 1, 1, 1, 1, 1, 1. So it's quite a huge number. So we would be working with this number later on. Okay, so the first thing to do to take into account, so with this default value, no matter what, we add the value of the target piece. And you remember that the piece code itself is already a piece value. That's the brilliancy behind the piece encoding that is used in this program. So you don't need to look up another variable which contains piece weights like we usually do. So piece weight is the piece code. This is so cool. So first we add the value of the target piece. Then we ask if the source square, so essentially where the piece we are about to move, it's being attacked by white. So the piece that we are moving, is it under attack or not? So this is what this line is questioning. If it is under attack, then we say evaluation plus equals the value of this source piece, which means that if we move the piece away, we would sort of win the piece. Yeah, so hence the evaluation goes up by the amount represented by the value of this source piece that we're moving. Another scenario, so it may happen that the target square is attacked by white, which means that we are about to lose a piece if we take a piece that is attacked by which is protected by another piece. So this condition prevents, say, queen taking the pawn that is protected by another pawn, let's say. So in this case, we just want to subtract from the evaluation, want to subtract the value of the source piece. Then we want to give an engine an idea of where he should develop its pieces. So this is known as the column evaluation, and this is known as the rank evaluation. So for the column evaluation, this seemingly tricky expression, which is described in great details in original dissection part of Alex's website, explains how this simple expression gives gives an idea for the engine that considering central columns is generally better. So it gives this +3 value to those squares that are closer to center. Not exactly closer to center, that's a bit complicated, it's a bit shifted. But anyway, this is trying to centralize pieces horizontally from the column perspective. And this simple line simply says that the higher rank the piece finds itself in, the better. So this gives the pawns an idea to get advanced and generally tries to put all the pieces the computer has to some places closer to opponent's key. So with these two simple lines of code, it essentially gives sort of an idea to the computer of developing pieces is a good thing, and he essentially tries to develop pieces, develops spawns, develops pieces, and even tries to go for an attack. So hope that kind of makes perfect sense. So this is another like genius idea how simple this can be. I was thinking about how to come up with not using the p-square tables, for instance, and this is how you can not use p-square tables in such an elegant way. A fantastic kind of thing, really. So finally, if the current evaluation is better than the best score, which by default is equal to 0, we just assign the best score to the best move found so far, and also we associate the best move, that is the best move, the move that is associated with the best score starts being equal to the current move we are looping over within the move list. So after this loop is done, we have the best move containing the move that scores the best score. So exactly like it happens in Minimax, but only for one side. It's not taken into account another side. So it may happen that Computer captures white key. This means the game is over, and we just detach the event listener in this case. So user cannot enter moves anymore. Also, it might happen the computer is about to move the pawn to the first rank, and this means he is about to promote. In this case, we want to convert black pawn to a black queen. Otherwise, this is just a regular move, which means we just want to move the piece from the source square to the target square, and we want to erase the source square. After this is done, computer move has been done on board. All we need to do is to render it so the user can see how computer has moved. And this line makes the chessboard being rendered initially. And this is essentially it, guys. So I really hope that this JavaScript implementation would shed some light on how this seemingly complicated, well, it's not seemingly complicated, it's extremely complicated piece of work, the state-of-art Guinness World Record holder program, 265 bytes, that allows to play chess just like we did over in here that I've been demonstrating. Also can be played on Alex Garcia's original website in the ZX Spectrum JavaScript emulator. And again, I really hope that my port would have some value towards understanding how original code essentially works. So leave alone the memory paging, leave alone the quirks and tricks related to Z80 assembly programming. Just take the bare algorithm, just take all the initial values that author has been using for evaluation, and just try to recreate exactly the same program but in a high-level language. And we got this. It's not as elegant as the original, not as small as the original, lots of text here really, but essentially this is the same program, and I'm so happy to have this program, and I would be even more happy if you guys use this program to learn how the world's smallest chess program actually works based on my JavaScript code. That's it from my side. Thanks for watching, and I'll see you in the next video. Until then, and cheers.